Assalamu alaikum and salam sejatera, everyone. My name is Nurul Hidayah Roslan, and I'm excited to welcome you to our course on Mechanics of Materials, an essential subject in civil engineering. In this class, we'll explore key concepts such as stress, strain, and deformation. We'll discuss how materials respond to various forces, including tension, compression, and shear. You'll learn how to analyze these forces and apply them to real-world scenarios, from bridges to buildings. We'll also delve into failure theories and the importance of material selection in engineering design. By the end of this course, you'll have a solid foundation in how materials function, which will be invaluable as you tackle more complex engineering challenges. Now, to give you a more visual understanding of these concepts, let's watch a video that dives deeper into the mechanics of materials.
You ever look up at a skyscraper and think, how the heck does that thing stand up? I mean, we're talking tons of steel, concrete, glass, all piled high like a Jenga game on steroids. It's enough to make a grown man sweat, just thinking about it. That's where the magic of engineering comes in, specifically a field called mechanics of materials. Yeah, it might sound boring, but trust me, this stuff is the backbone of everything we build. From bridges that span rivers to dams that hold back oceans. Think of it like this. Every material, whether it's steel, concrete, or even a simple brick, has its limits. Push it too far and it'll buckle, crack, or worse. The trick is knowing those limits, knowing how much stress a material can handle before it says, enough is enough. That's what mechanics of materials is all about. Understanding how materials behave under pressure, literally. It's like being a therapist for building materials, figuring out their strengths, their weaknesses, and what makes them tick. Now, I'm not an engineer, but I've worked with enough of them to know they don't mess around when it comes to safety. And when you're talking about structures that people rely on every day, safety is job one. That's where mechanics of materials comes in. It gives engineers the tools they need to predict how a material will behave under different loads and conditions. They use fancy equations and computer models, but it all boils down to this. Will this bridge hold the weight of all those cars? Will this building withstand a hurricane? It's not just about making sure things don't fall apart either. Mechanics of materials also helps engineers design structures that are efficient and economical. Nobody wants to build a bridge that's 10 times stronger than it needs to be, right? That's just a waste of time, money, and resources. So next time you walk across a bridge, drive through a tunnel, or even just sit in your house, take a moment to appreciate the unsung hero of it all. Mechanics of materials. It's the silent guardian, the watchful protector, making sure our built environment doesn't come crashing down around us. Let's get down to the nitty-gritty. One of the key tools in mechanics of materials is the stress-strain curve. This might sound complicated, but it's actually pretty simple. Imagine taking a rubber band and stretching it. The more you pull, the more it stretches, right? That's essentially what a stress-strain curve shows. Stress is like the force you're applying to the rubber band, and strain is how much it stretches. The curve tells you how much a material can stretch or compress before it breaks. It's like a material's autobiography, revealing its strength, elasticity, and ultimately, its breaking point. Each material has its own unique curve, kind of like a fingerprint. Steel, for example, is like that tough guy at the gym who can handle a lot of weight. It has a high stress limit before it starts to deform permanently. Concrete, on the other hand, is more like that guy who's still working his way up to the heavy weights. Understanding these curves is crucial for engineers. It helps them choose the right material for the job and design structures that can withstand the stresses and strains of everyday life. Now, let's talk about some real-world examples. Think about a suspension bridge, like the Golden Gate Bridge. That thing is constantly under stress from traffic, wind, even its own weight. Engineers use mechanics of materials to calculate exactly how much stress each cable and beam will experience, and make sure they're strong enough to handle the load. Or how about skyscrapers? These towering giants have to withstand wind loads, seismic activity, and even the weight of the people and furniture inside. Mechanics of materials helps engineers design buildings that can sway slightly in the wind without collapsing, making them safer and more comfortable for the people inside. And then there are dams, holding back massive amounts of water with nothing but their own strength. Engineers use mechanics of materials to analyze the stresses within the dam's structure, ensuring it can withstand the immense pressure of the water it holds back. These are just a few examples of how mechanics of materials is used every day to design and build the structures we rely on. It's the invisible force that keeps our world standing.
An exciting semester together.